Hello, guys, and welcome to another episode of Nugget of the Day. This is Nugget 8, a presentation of Regional for Trainees. In this Nugget, we focus on inverse square law of peripheral nerve stimulation. So, let's get into it and learn what this inverse square law is. Now, there are different inverse square law which we come across in physics. And initially, the inverse square law was to do with electromagnetic forces or the electrical forces and charges. This law was proposed by Coulomb, and what he stated was that I is equal to a product of K, which is a constant, and I, which is minimal current, divided by R square, which is the square of the distance. Capital I representing the current intensity at a given membrane or at a given point, K representing constant, I representing minimum current required to stimulate a tissue like a nerve, and R representing the distance. Simply put, the current intensity is inversely proportional to the square of the distance between a stimulating electrode and a given point. And therefore, because this relationship is inverse and because it is inversely related to the square of the distance, is called the inverse square law. Let's have a deeper understanding into this particular law. Let's try and understand this law by looking at a given needle shown here by the arrow on the left and a given nerve shown by this round structure on the right. And let's assume the distance between the stimulating needle and the nerve is represented by R. If a given voltage V is applied across the needle, then we see that the current intensity produced at the nerve, which is responsible for stimulation of the nerve, is inversely proportional to the distance between the nerve and the needle. And therefore, as we bring the needle closer, as shown in this diagram, say let's reduce the distance by half, keeping the voltage constant, then according to the inverse square law, the new current intensity by reducing the distance to half is going to get multiplied by 4 times. And therefore, as we reduce the distance of the nerve and needle distance, in this case reducing it by 50%, we get an increase in intensity of the current at the nerve by over 400%. And basically this means that we are going to get a very high amount of motor stimulation and muscle contraction at the nerve end. Now let's quickly have a look at what is the practical application or the inference of this law. How do we actually use this in practice? Now, as we are performing a peripheral nerve stimulation and we introduce a needle and are moving towards the nerve tissue, the current intensity at the nerve increases, resulting in more vigorous muscle stimulation, and it becomes easier to stimulate the nerve as our needle approaches the nerve. Now, this vigorous muscle contraction can be quite painful to the patient. So, what we don't want is to cause pain to the patient, and therefore we drop our voltage applied to the needle so that we can maintain the current intensity, and therefore we commonly start with 2 milliamperes but quickly drop it down to 0.5 milliamperes, maintaining the current intensity at the nerve. This can be better understood by this diagram, which shows on the y-axis the stimulation current and on the x-axis the distance of the needle from the nerve. Let's assume this is 0 centimeters and 0.5 centimeters on either side and 1 centimeters to further out. It's not very difficult to understand that when the needle and nerve distance is minimal, say 0, then you're going to need the least amount of current to stimulate the nerve, which is commonly practical accepted to be about 0.5. And as we go away from the nerve, you're going to need more current. So when a needle approaches from far away, the current required quickly decreases. And as the needle crosses over and overshoots, again we need more current to stimulate the nerve. So that is it. And until next time, adios amigos.